Hello everyone, in this tutorial I will teach you to use effective computer vision techniques with OpenCV and Python, ultimately to detect lane lines for a simulated self-driving car. This video was done in collaboration with the Programming Knowledge YouTube channel, and by the time you finish this tutorial, if you're interested in more self-driving car content, feel free to check out the link in the description below, but without further ado, let's start this tutorial. Welcome to your first lesson. This lesson is quite simple, as all we're going to be doing is installing the Anaconda distribution. We'll start this off by going over to anaconda.com/download. The Anaconda distribution conveniently installs Python, the Jupyter Notebook app, which we're going to use quite often throughout this course, and over 150 other scientific packages. Since we're installing Python for Mac, make sure to navigate to the Mac section. And we're going to install Python 3, not Python 2. It's very likely that you're seeing different versions of Python than the ones I'm seeing right now. But regardless, since Python 2 is no longer being updated, it's imperative that you download the latest version, Python 3, to keep compatibility with future Python improvements, and to also follow along with this course. Click on the download button. No thanks. Once your download is finished, we'll open this package. Continue. Keep pressing continue. Continue. Agree to the terms and conditions that you have read the agreement, and simply enough, press install. Once your installation is complete, press continue again, close, and move to trash. That is all, very easy and intuitive. To ensure that this works, whatever terminal window you had previously opened, make sure to close it. I already had one open, so I'll close mine. If you don't have one open, then you should be fine. What we'll do is we'll open up a new terminal window by performing a spotlight search, which you can do by pressing Command and space, write terminal, and press enter. Alternatively, you could have just accessed your terminal by pressing on F4 and performing the search here. But regardless, to ensure a successful installation, write the command python 3 /version. And I get a version of 3.6.4. Make sure you also get a Python 3 version. That is all. Hope you were able to follow along. If you have any issues with the installation, feel free to ask me in the Q&A section. Welcome back. We'll be making use of the Atom text editor in the computer vision section. You can feel free to use any text editor you want, like Sublime or Vim, in which case feel free to skip this lesson. Otherwise, if you don't have a text editor installed, let's get to it. Downloading it is quite simple for both Mac and Windows. I'll be proceeding with the Mac installation by going over to atom.io, and inside of atom.io just clicking download. This is also downloadable from TextBot by also going over to Google and then searching TextBot Atom download. And going into the first link, where if you just simply click on the appropriate link and then wait for it to finish setting up the download, whether you're on Mac or Windows. Alright, once your installation is complete, it should be inside of your Downloads folder. Let us just open up Atom and see what it's like. It's verifying this new application. We're going to open it. Alright, we're going to close the following, and now what we'll do is click on Packages. And inside of Packages, we're going to go to Settings View and open the Settings. If you're using a PC, I imagine the process to get to your settings view should be quite similar. And now, inside of Editor, we can modify some settings. For example, the font family. I'm quite satisfied with the current font, and font size 16 seems pretty reasonable. And two other boxes I like to have checked are showing the cursor on selection and showing indentation indicators. Indentation is fundamental to Pythonic code, as it distinguishes between different blocks of code. So it will definitely be useful to always have indentation indicators. And finally, one more thing that's pretty important is the tab length. The default tab length should be 2, I believe, but I personally prefer using 4 spaces per tab. And just one more thing I want to do before moving on is enabling autosave. So we'll go back to Package, and this will be very convenient in our code since it would keep us from having to save our code every time we need to run it. So what we'll do is inside of Core Packages, scroll down till you find autosave. Right over here, and make sure that you enable it. I already have it enabled. Alright, and that concludes the installation section. The purpose of this section is to build a program that can identify lane lines in a picture or a video. When you and I drive a car, we can see where the lane lines are using our eyes. A car doesn't have any eyes, and that's where computer vision comes in, which through complex algorithms helps the computer see the world as we do. In our case, we'll be using it to see the road and identify lane lines in a series of camera images. This lesson in particular will be quite simple, as all we're going to do is set up the initial stages of our project and display an image, onto which we'll be identifying lane lines. You'll start by opening up your terminal or command prompt and navigate to the desktop directory with the command cd desktop. Change directory desktop. Inside of desktop, we'll make a new folder with the command mkdir, make directory finding lanes. This folder you just made inside of desktop, you're going to open up with Atom by going to File, Open, Desktop, Finding Lanes. Inside of Finding Lanes, make a new Python file called lanes.py. Inside of the lanes file, we're going to start by writing a program that can identify lanes in a JPEG image. I posted the image on my GitHub. To access it, make sure to go to the following link. The link is also available in the description below. And so once you get to this GitHub page, click on testimage.jpg. And what we're going to do is actually download the image, or better yet, just save the image, and make sure to save it as a JPEG image. It doesn't matter where you save it, and make sure this says test image such that there are no extra 1s or 2s in there, so that your naming remains consistent with what I have in the videos. Alright, save your image. Once you download it, wherever you have it downloaded, make sure to drag it into your project folder like so. And now to display the image, we're going to use OpenCV, an open source computer vision library. So inside of your terminal, we're going to write the command pip install. We'll make use of the package manager pip to install OpenCV-contrib-python. Once you're finished installing it, back to Visual Studio, we're going to import the library CV2. And from this library, for now, we will access two functions, imread and imshow. To load our image, we'll first make use of the imread function by setting image is equal to cv2.imread, and in this argument is where you will specify the image, the file name, as a string. Ours is testimage.jpg. And what this function will do is read the image from our file and return it as a multi-dimensional NumPy array containing the relative intensities of each pixel in the image. We now have our image data in a NumPy array. The next step is to actually render it with the imshow function. So we'll write cv2.imshow. This takes in two arguments. The first one is the name of the window that we're going to open up. We'll just call it result. And the second argument is the image that we want to show itself. If I run the code now to my terminal, navigate to my project folder by writing cd, our project is named Finding Lanes, and run the Python file, python lanes.py, Notice that nothing is going to happen. That's because this function should be followed by the waitKey function, cv2.waitKey, and what this function does is it displays the image for a specified amount of milliseconds. We'll set a time of 0. What this will do is it will display our window, our results window, infinitely until we press anything in our keyboard. If we rerun the code, Python lanes, the image is displayed, and notice our window name results. We'll keep this lesson short and stop here. You learn how to load and display images using the OpenCV library. In the next lesson, we'll start discussing canny edge detection, a technique that we'll use to write a program that can detect edges in an image, and thereby single out the lane lines. Welcome to lesson number 2. The goal of the next few videos will be to make use of an edge detection algorithm, the canny edge detection technique. The goal of edge detection is to identify the boundaries of objects within images. In essence, we'll be using edge detection to try and find regions in an image where there is a sharp change in intensity, a sharp change in color. Before diving into this, it's important to recognize that an image can be read as a matrix, an array of pixels. A pixel contains the light intensity at some location in the image. Each pixel's intensity denoted by a numeric value that ranges from 0 to 255. An intensity value of 0 indicates no intensity if something is completely black, whereas 255 represents maximum intensity, something being completely white. That being said, gradient is the change in brightness over a series of pixels. A strong gradient indicates a steep change, whereas a small gradient represents a shallow change. On the right-hand side, you're looking at the gradient of the soccer ball. The outline of white pixels corresponds to the discontinuity in brightness at the points, the strength in gradient. This helps us identify edges in our image, since an edge is defined by the difference in intensity values in adjacent pixels. And wherever there's a sharp change in intensity, a rapid change in brightness, wherever there's a strong gradient, there is a corresponding bright pixel in the gradient image. By tracing out all of these pixels, we obtain the edges. We're going to use this intuition to detect the edges in our road image. This is a multi-step process. Step 1 being to convert our image to grayscale. Why convert it to grayscale? Well, as we discussed earlier, images are made up of pixels. A 3-channel color image would have red, green, and blue channels. Each pixel a combination of 3 intensity values, whereas a grayscale image only has 1 channel, each pixel with only 1 intensity value, ranging from 0 to 255. The point being, by using a grayscale image, processing a single channel is faster than processing a 3-channel color image, and less computational intensive. Let's start implementing this inside of Atom. We've already loaded and read our image into an array. Now what we'll do is import numpy as the alias np. We're going to work with a copy of this array by setting lane image is equal to numpy.copy image, thus copying our array into a new variable. It's imperative that you actually make a copy of this array instead of just setting lane image is equal to image. If we do this, any changes we make to lane image will also be reflected in the original mutable array. Always ensure that you make a copy whenever working with arrays, instead of just setting them equal directly. So what we'll do now is we'll create a grayscale from the color image. We'll do that by setting variable gray is equal to cv2, and from our OpenCV library, we'll call the function cvtColor, which converts an image from one color space to another. We'll be converting lane image, and in the second argument, for an RGB to grayscale conversion, we can use the flag cv2 dot color underscore RGB to gray. Very intuitive. And now, instead of showing the color image, we'll show the grayscale image. If we go to our terminal, Python lanes.py, everything works out accordingly. This was step number 1. Step number 2 of edge detection will be to next apply a Gaussian blur on this image. Let's talk about that in the next video. Welcome to lesson number 3. In the last lesson, we applied step number 1, which was to convert our image to grayscale. Step 2 is to now reduce noise and smoothen our image. When detecting edges, while it's important to accurately catch as many edges in the image as possible, we must filter out any image noise. Image noise can create false edges and ultimately affect edge detection. That's why it's imperative to filter it out, and thus smoothen the image. Filtering out image noise and smoothing will be done with a Gaussian filter. To understand the concept of a Gaussian filter, recall that an image is stored as a collection of discrete pixels. Each of the pixels for a grayscale image is represented by a single number that describes the brightness of the pixel. For the sake of example, how do we smoothen the following image? The typical answer would be to modify the value of a pixel with the average value of the pixel intensities around it. Averaging out the pixels in the image to reduce noise will be done with a kernel. Essentially, this kernel of normally distributed numbers is run across our entire image and sets each pixel value equal to the weighted average of its neighboring pixels, thus smoothing our image. We're not going to go over kernel convolution and how it does it. Just know that when we write this line of code inside of our editor, blur is equal to cv2.Gaussian blur, what we're doing is applying a Gaussian blur on a grayscale image with a 5x5 kernel. The size of the kernel is dependent on specific situations. A 5x5 kernel is a good size for most cases. But ultimately, what that will do is return a new image that we simply called blur. Applying the Gaussian blur by convolving our image with a kernel of Gaussian values reduces noise in our image. Back to our project, set blur is equal to cv2.Gaussian blur. We'll apply this blur on our grayscale image with our 5x5 kernel, and we'll just leave the deviation as 0. The main thing you should take away from this is that we're using a Gaussian blur to reduce noise in our grayscale image. And now we'll simply show the blurred image. If we run this code, Python lanes.py, there is our blurred grayscale image. Later on, when we apply the canny method, it should be noted that this step was actually optional, since the canny function is going to internally apply a 5x5 Gaussian when we call it. Regardless, now we know the theory, we've obtained our grayscale, we've smoothened it and reduced noise with a Gaussian blur. Now it's time to apply the canny function. We'll do that in the next video. In the last lesson, we smoothened our image and reduced noise. Now it's time to apply the canny method to identify edges in our image. Recall that an edge corresponds to a region in an image where there is a sharp change in intensity, or a sharp change in color between adjacent pixels in the image. The change in brightness over a series of pixels is the gradient. A strong gradient indicates a steep change, whereas a small gradient, a shallow change. We first established that an image, as it's composed of pixels, can therefore be read as a matrix, an array of pixel intensities. To compute the gradients in an image, one must recognize that we can also represent an image in a two-dimensional coordinate space, x and y. The x-axis traverses the image's width, and the y-axis goes along the image's height. Width representing the number of columns in the image, and height the number of rows, such that the product of both width and height gives you the total number of pixels in your image. The point being, not only can we look at our image as an array, but also as a continuous function of x and y. Since it's a mathematical function, we can perform mathematical operation, which begs the question, what operator can we use to determine rapid changes in brightness in our image? What the canny function will do for us is perform a derivative on our function in both x and y directions, thereby measuring the change in intensity with respect to adjacent pixels. A small derivative is a small change in intensity, whereas a big derivative is a big change. By computing the derivative in all directions of the image, we're computing the gradient. Since recall, the gradient is the change in brightness over a series of pixels. So when we call the canny function, it does all of that for us. It computes the gradient in all directions of our blurred image, and is then going to trace our strongest gradients as a series of white pixels. But notice these two arguments, low threshold and high threshold. Well, this actually allows us to isolate the adjacent pixels that follow the strongest gradients. If the gradient is larger than the upper threshold, then it is accepted as an edge pixel. If it is below the lower threshold, it is rejected. If the gradient is between the thresholds, then it will be accepted only if it is connected to a strong edge. The documentation itself recommends to use a ratio of 1:2 or 1:3. As such, we'll use a low-high threshold ratio of 1:3, 50:150. Now that we know what goes on under the hood, we can call this function inside of our project by writing canny is equal to cv2.canny. We'll apply the canny method on the blurred image with low and high thresholds of 50 and 150. And now we'll show the image gradient instead of the blurred image, canny. If we go ahead and run the code, Python lanes.py, and there's the gradient image, which clearly traces an outline of the edges that correspond to the most sharp changes in intensity. Gradients that exceed the high threshold are traced as bright pixels, identifying adjacent pixels in the image with the most rapid changes in brightness. Small changes in brightness are not traced at all, and accordingly they are black, as they fall below the lower threshold. That's it for the canny method. We used it to outline the strongest gradients in our image. Now this was a lot of explanation for just 3 lines of code, but it's good to have a grasp of what's going on under the hood before we proceed any further. Now that we've computed the strongest gradients, in the next few videos we'll apply the Hough Transform method to detect our lanes. In the last lesson we used the canny function to outline the strongest gradients in our image. Now we'll focus on how we can identify lane lines in the image. Before doing that, what we'll do now is specify a region of interest in our image that we're going to use to detect our lane lines as currently shown. Before proceeding any further, what we'll do first is actually wrap our code inside of a function by defining a function, canny, which takes in an image. And what we'll do is copy the canny algorithm code inside of the function. And specify canny as the return value, return canny. And what we can do now is simply set canny equal to the return value of our canny function, passing in the initial RGB color image, and rerunning this code back into our terminal, Python lanes.py. Everything is still intact. What we'll do now is we'll specify this area as a region of interest. Before doing so, instead of showing our image gradient with OpenCV, we'll use the matplotlib library to better clarify how we're going to isolate this region. You should already have matplotlib installed courtesy of the Anaconda distribution, so what we can do now is import matplotlib, and we're going to need the subpackage from matplotlib called pyplot as an alias plt. Conveniently, pyplot contains the function imshow, so we can just replace cv2 with plt, and in this case, no need to specify a window name, just the image. The equivalent of OpenCV's wait key function would simply be plt.show. If we go back and run the code in our terminal, Python lanes.py, we get the same image along with x and y axes. Notice how the y-axis starts from the first row of pixels and then goes downwards. With our axes, we're going to limit the extent of our field of view based on the region of interest, which ultimately traces a triangle with vertices of 200 along the x and 700 pixels along the y, which would simply be the bottom of the image, 1100 pixels along the x, and once again the bottom of the image, 700 pixels at the y, the very bottom. And the last vertex will simply be 550 pixels along the x and 250 traveling down the y, ultimately tracing a triangle that isolates the region where we want to identify the lane lines. So the goal of this video will be to create an image that's completely black, a mask, with the same dimensions as our road image, and fill part of its area with a triangular polygon. First and foremost, we'll revert showing the image to being done with OpenCV rather than matplotlib. And what we'll do now is define a function, def region of interest, which also takes in an image. And what this function will do is pretty self-explanatory. It will return the enclosed region of our field of view, and recall that the enclosed region was triangular in shape. So we'll set a variable named triangle is equal to, and this polygon, this triangle, will declare as a numpy array, np.array. Inside of this array is where you specify its vertices. Recall that while limiting the extent of our field of view, we traced a triangle with vertices that go 200 along the x, and vertically until the extent of our image, until the bottom, which in this case is the height. We can get the height of our image by setting height is equal to image.shape at the index 0. Recall from the NumPy crash course that the shape of an array is denoted by a tuple of integers. Since we're dealing with a two-dimensional array, the first integer corresponding to the number of rows, the y-axis traverses the image's height, and height accordingly is the number of rows. So you can already assume that this value will be something very close to 700, since that's what we saw in matplotlib. So we'll simply set the height to complete our first vertex, the second one being 1100 pixels along the x, and vertically, once again, right up until the extent of our image being the height, the vertical extent. And lastly, the last vertex was 550 pixels along the x and 250 pixels along the y. This polygon, we're going to apply it onto a black mask with the same dimensions as our road image. So we'll set mask is equal to numpy dot zeros like image. Recall that an image can be read as an array of pixels. Zeros like creates an array of zeros with the same shape as the image's corresponding array. Both arrays will therefore have the same number of rows and columns, which means that the mask will have the same amount of pixels and thus the same dimensions as our canny image that we're going to pass in a bit. Although its pixels will be completely black, as all of them will have zero intensity. What we have to do now is fill this mask, this black image, with our polygon using OpenCV's fill poly function. That is cv2.fill_poly. We will fill our mask with our triangle. The third argument specifies that the color of our polygon, which we're going to have be completely white. So what we're going to do is take a triangle whose boundaries we defined over here and apply it on the mask such that the area bounded by the polygonal contour will be completely white. What we'll do now is return our modified mask, return mask, and instead of showing the canny image, we'll be showing the return value of our function, region of interest, and the image that we're going to pass in is simply going to be the canny image. Let's run the code. Let's run python lanes.py, and it would throw an exception. And that's because fillPoly, the fillPoly function, fills an area bounded by several polygons, not just one. Even though you and I both know that we're dealing with only a single polygon, we'll rename this variable from triangle to polygons for consistency, and we'll set it equal to an array of polygons. In our case, an array of simply one polygon. Change this from triangle to polygons. If we rerun this code, there's our mask. And inside of the mask, there is the enclosed region, the polygon with the specified vertices. Now you might be asking yourself, why did we go through all of this? Well, this video has gone on long enough, so let's talk about that in the next lesson. Previously, we created a mask with the same dimensions as our road image. We then identified a region of interest in our road image with very specific vertices along the x and y axis that we then used to fill our mask. The image on the right, why is it important? Well, we're going to use it to only show a specific portion of the image. Everything else we want to mask. So to understand how we're going to use this image to mask our canny image, to only show the region of interest traced by the triangular polygon, you'll require a basic understanding of binary numbers. If you're already familiar with binary numbers, feel free to skip the next 2 minutes or so of this video. Otherwise, I'll introduce it now, and I'll do it very quickly. Commonly, when one thinks of binary representations, they think of zeros and ones. Well, more specifically, binary numbers are expressed in the base 2 numeral system, which uses only 2 symbols, typically zeros and ones. What does that mean? For example, the number 23. Its binary representation is 10111. How did I obtain that number? Well, let's imagine 8 placeholders, 8 boxes. As we're dealing with a base 2 numeral system, each box represents a power of 2. Each numerical place will correspond to an increasing power of 2. The first box, 2 to the power of 0, which simply equals 1, then 2 to the power of 1, which equals 2, all the way up until 2 to the power of 7, up until 128. We'll come back to this. Now each box can only accept one of 2 values, 0 or 1. So we want to put in binary the number 23. We wish to represent this number in binary format. So what we do is we start with the highest value, 128, and ask ourselves, is this value in the number 23? 128 is clearly not in the number 23, it's way too big, so we leave that as 0. 64 is not in 23, we also leave that as 0. 32 is certainly greater than 23, we leave that as 0. 16, this goes into 23, so it's assigned the number 1. And so far we've used up 16, 23 minus 16 equals 7. There's 7 left we have to account for. Does 8 go into 7? Nope, we leave that as 0. Does 4 go into 7? Of course, that takes a value of 1. So now we've used up 4, 7 minus 4 equals 3, and there's 3 left that we have to account for. Does 2 go into 3? Yep. Now there's only 1 left. Does 1 go into 1? Indeed. And there's the binary representation of 23. We can cut off the zeros in the beginning, and it's just as we said earlier, 10111. Alright, so why did I just randomly start talking about binary numbers? Well, the image on the right, I went ahead and printed out its pixel representation. I resized the array simply because it was too large. But never mind that. Notice how the triangular polygon translates to pixel intensities of 255, and the block surrounding region translates to pixel intensities of 0. What's the binary representation of 0? Well, none of these numbers go into 0. So we leave 0 for each placeholder, leaving us with a binary representation of 0, 0, 0, 0. What about 255? Well, for that we'll need 8 placeholders, 2 to the 0 up until 2 to the 7, and so if you do the math we just talked about, you'll realize that its binary representation is all ones. 8 ones, as all of these numbers add up exactly to obtain 255. As a side note, if we think of this in terms of bits, where each bit holds a single binary value, and 8 bits form 1 byte, 255 is actually the maximum representable value by an 8-bit byte. So we can conclude since the surrounding region is completely black, each pixel with a value of 0, then the binary representation of every pixel intensity in that region would be all zeros. 0, 0, 0, 0. As for the polygonal contour, whose region is completely white, then the binary representation of every pixel intensity in that region would be all ones. Why is this important? Well, we're going to apply this mask onto our canny image to ultimately only show the region of interest, the region traced by the polygonal contour. We do this by applying the bitwise AND operation between the two images. The bitwise AND operation occurs elementwise between the two images, between the two arrays of pixels. Now both of these images have the same array shape and therefore the same dimensions and the same amount of pixels. By applying the bitwise AND, since it occurs elementwise, then we're taking the bitwise AND of each homologous pixel in both arrays. And the way bitwise AND works is, let's imagine two binary numbers, 011001, which, if you do the math you saw earlier, you'll realize is the number 25, and 110010, which would be the number 50. This is a pretty standard example, but regardless, let's take their bitwise AND, and what AND will do is it puts a 0 unless both pairs are 1s. In the first pair, since one of these is 0, we put a 0. In the second one, both of them are 1s, so we put a 1. In this one of them is 0, so we put a 0, and we keep doing this until eventually the resultant AND operation would yield 010000. What if we took the bitwise AND of all zeros with any other value? Well, no matter what, during the operation, you're always going to have at least one 0, which means the result of the AND operation will yield all zeros, no matter what value we choose to operate against it. So going back to our two images, the black region whose pixels have intensity values which correspond to the binary number we just talked about, 0000, by taking the bitwise AND, by operating it against the pixel values in the corresponding region of the other array, the result is always going to be a binary value of 0000. This translates to the number 0, which means all pixel intensities in that region will have a value of 0. That's what the result's going to be. They will be completely black, thereby masking the entire region. We know the operation occurs element-wise, so all the white pixels in this region of the array will be operated against the corresponding region of the other array. Well, this region will remain unaffected. Why, you might ask? Well, we already concluded that since the polygonal contour is completely white, then the binary representation of each pixel intensity in that region would be all 1s. If you take the bitwise AND of the 1s with any other binary value, it's not going to have an effect. We could try this out. As we take the bitwise AND of these two values. Two 1s, so we put a 1 here, same case here, here, and here, and we keep doing this to obtain the following results, which notice is the same as one of our values, meaning that taking its bitwise AND with the 1s didn't have an effect. And so in our image, taking the bitwise AND of these two regions would also have 0 effect, which means we've successfully masked our canny image to ultimately only show the region of interest, the region traced by the polygonal contour. We can implement this by setting masked image is equal to cv2.bitwise AND, and we'll compute the bitwise AND of both the canny and mask arrays. This universal function implements the Python operator AND, finally, we'll return masked image, and we'll just set cropped image is equal to the return value of region of interest, We'll pass in the candy image as we did in the previous video, and we'll show the cropped image instead. Back to our terminal, Python, lanes.py, and everything worked out accordingly. We isolated the region of interest and masked everything else. The final step of lane detection will be to use the Hough Transform technique to detect straight lines in our region of interest, and thus identify the lane lines. So far, we've identified the edges in our image and isolated the region of interest. Now we'll make use of a technique that will detect straight lines in the image and thus identify the lane lines. This technique is known as Hough Transform. We'll start by drawing a 2D coordinate space of x and y, and inside of it a straight line. We know that a straight line is represented by the equation y is equal to mx plus b. Nothing new so far, just simple math. Our straight line has two parameters, m and b. We're currently plotting it as a function of x and y, but we can also represent this line in parametric space, which we will call Hough space, as b versus m. We know the y-intercept of this line is 2, and the slope of the line is simply rise over run, the change in y over the change in x, which evaluates to 3. Given the y-intercept and slope, this entire line can be plotted as a single point in Hough space. Now imagine that instead of a line, we had a single dot, located at the coordinates 12 and 2. There are many possible lines that can pass through this dot, each line with different values for m and b. You could have a line that crosses it with m and b values of 2 and 8, 3 and 6, 4 and 4, 5 and 2, 6 and 0, so on and so forth. Notice that a single point in x and y space is represented by a line in Hough space. In other words, by plotting the family of lines that goes through our point, each line with its own distinct m and b value pair, this produces an entire line of m and b value pairs in Hough space. What if we also had a point at 8 and 1? Once again, there are many lines that can cross this point, each line with different values for m and b. All of these different values for m and b represented by a line in parametric space. The point being, whenever you see a series of points, and we're told that these points are connected by some line, ask yourself this question: what is that line? As previously mentioned, there are many possible lines that can cross each point individually, each line with different slope and y-intercept values. However, there is one line that is consistent with both points. We can determine that by looking at the point of intersection in Hough space, because that point of intersection represents the m and b values of a line consistent with crossing both of our points, which in this case has slope and y-intercept of 4. Suppose there is one more point in our image space, at the point 16 and 3. This point is also represented by a line in parametric space. Each point in that line denotes different values for m and b, which once again correspond to different lines that can pass through this point. But notice that there is another intersection at the same point, which means that the line with the following slope and y-intercept 4 and 4 crosses all three of our dots. Why is this relevant? Well, this idea of identifying possible lines from a series of points is how we're going to find lines in our gradient image. Recall that the gradient image is just a series of white points which represent edges in our image space. You and I can look at the various series of points in our image and automatically assume these points belong to a line, this series of points belongs to a line, so on and so forth. But what are the lines? What are their parameters? How do we identify them? Well, take these 4 points for example in our image space, which correspond to the following Hough space. What we're going to do is first split our Hough space into a grid, each bin inside of our grid corresponding to the slope and y-intercept value of a candidate line. For example, what if I told you these points belong to a line? What is that line? Well, I can see that there's points of intersection here, there's some here, and some here as well. Well, all of these points of intersection are inside of a single bin. For every point of intersection, we're going to cast a vote inside of the bin that it belongs to. The bin with the maximum number of votes, that's going to be your line. Whatever M and B value that this bin belongs to, that's the line that we're going to draw since it was voted as the line of best fit in describing our data. Now that we know the theory of how we're going to identify lines in our gradient image, you would think to yourself, alright, enough talking, time to code. Well, not so fast. There's just one tiny problem. We still haven't taken into account vertical lines. Obviously, if you try to compute the slope of a vertical line, the change in x is 0, which ultimately will always evaluate to a slope of infinity, which is not something that we can represent in Hough space. Infinity is not really something we can work with anyway. We need a more robust representation of lines so that we don't encounter any numeric problems, because clearly this form, y is equal to mx plus b, cannot represent vertical lines. That being said, instead of expressing our line with Cartesian coordinate system parameters m and b, we'll instead express it in the polar coordinate system rho and theta, such that our line equation can be written as rho is equal to x cos theta plus y sine theta. If you're really interested in how this equation is derived, feel free to ask me in the Q&A, but the main idea is that this is still the equation of a line, but in polar coordinates. If I am to draw some line in Cartesian space, the variable rho is the perpendicular distance from the origin to that line, and theta indicates the angle of inclination of the normal line from the x-axis, which is measured in radians clockwise with respect to the positive x-axis. Let's look at some examples. Suppose I had a point with x position 5 and y is equal to 2. As you know, this is a point, and many lines can pass through this point, including a vertical line. We used to define lines passing through our points by their slope and y-intercept m and b, but now they will be defined based on rho and theta. If we want to measure the perpendicular distance from the origin to the top of the line, the angle of inclination of the normal line from the axis is simply 0, which works out to a distance of 5. Another possible line that could pass through our point is a horizontal line. The perpendicular distance from the origin to our line would correspond to an angle of 90 degrees, which in radians is pi over 2, which ultimately works out to a distance of 2. This line, therefore, is characterized by an angle theta of pi over 2 and a distance rho of 2. Just to strengthen our knowledge, another possible line is the following, whose perpendicular distance from origin to our line corresponds to an angle of 45 degrees from the positive axis. That is pi over 4 radians, which works out to a distance rho of about 4.9. The point of all this being is that previously a point in image space represented a line in Hough space. Whereas now with polar coordinates for a given point, by plotting the family of lines that go through it, each line with a distinct value for theta and rho, we get a sinusoidal curve. This curve represents all of the different values for rho and theta of lines that pass through our point. This might look a bit intimidating, but the concept is the exact same. Because imagine instead of 1 point, we had 10 points, which in turn results in 10 sinusoidal curves. As previously noted, if the curves of different points intersect in Hough space, then these points belong to the same line, characterized by some rho and theta value. So just like before, a line can be detected by finding the number of intersections between curves. The more curves intersecting means that the line represented by that intersection crosses more points. In our case, all 10 of our curves intersect at a single point, which means that there is a single line with some rho and theta value that crosses all 10 of our dots. We can look at a more specific example with 3 dots in our Cartesian, which represent the following sinusoidal curves. All 3 lines intersect at the same point, characterized by a theta value of 0.92 radians and perpendicular distance of about 9.66. So that's the idea, finding which line best fits our data. In our case, it's the one with the following parameters. We can also apply the concept of voting that we discussed earlier, such that our Hough space is still in the form of a grid. And obviously, this bin would have the maximum number of votes. And just like before, the bin with the maximum number of votes, that's going to be your line. Whatever theta and r value that this bin belongs to, that's the line that we draw since it was voted as the line of best fit in describing our data. Later on, when we start implementing this, we'll talk about the concept of thresholds. But for now, that is all for Hough Transform. We're just trying to find the lines that best describe our points. And that's what we're going to use to find the lines that best define the edge points in our gradient image. Let's start implementing that in the next video. Previously, we looked at the theory behind detecting possible lines from a series of points by looking at the bin with the maximum number of votes. That is, the maximum number of intersections inside the bin. We discussed that the bin with the maximum number of votes is the line we draw through a series of points. Whatever theta and r value that this bin belongs to, that's the line we draw since it was voted as the line of best fit in describing our data. We'll start implementing this by detecting lines in the cropped gradient image by setting lines is equal to cv2.houghLines p. The first argument is the image where you want to detect lines, which would simply be our cropped image. The second and third arguments specify the resolution of the Hough accumulator array. The Hough accumulator array, previously I described as a grid for simplicity, but it's actually a 2-dimensional array of rows and columns, which contain the bins that we're going to use to collect votes, with each bin representing a distinct value of rho and theta. The second and third arguments are really important as they specify the size of the bins. Rho is the distance resolution of the accumulator in pixels, and theta is the angle resolution of the accumulator in radians. The larger the bins, the less precision in which lines are going to be detected. For example, imagine every bin in our array was so large, this is way too coarse in the sense that too many intersections are going to occur inside of a single bin. We need our bins to be sufficiently small. The smaller the row and degree intervals we specify for each bin, the smaller the bins, and the more precision in which we can detect our lines. Yet you don't want to make your bins too small, since that can also result in inaccuracies and takes a longer time to run. So what we'll do is we'll specify a precision of 2 pixels accompanied by a 1 degree precision. This needs to be in radians. 180 degrees is equal to pi radians, so 1 degree will simply be pi over 80. That is numpy.pi divided by 180, 1 radian. To demonstrate the effect of this early on, here's a sneak peek of the end result when we finally detect our lines. In this picture, the bin resolution was a row of 20 pixels and 5 degrees, whereas here it's 2 pixels with a single degree precision. Clearly this one is much more precise in its output. So that's it for resolution. The fourth argument is very simple. It's the threshold. To find and display the lines from a series of dots, we need to find the bins with the highest number of votes, right? Once you find that bin, you take its theta and rho value and plot the line. However, how do we know which bins to choose? What's the optimal number of votes where we can say, okay, draw the line that corresponds to this bin? Well, that's where the threshold comes in. Threshold is the minimum number of intersections needed to detect a line. As previously mentioned, in a series of points, the points of intersection in Hough space represent the theta and rho values of lines that are common between a series of points. For every point of intersection, a vote is cast inside of the bin that it belongs to, which represents a line with some value for rho and theta. There's 5 intersections here, so 5 votes, and we assign a threshold of 3. The number of votes in this case exceeds the threshold, and it is therefore accepted as a line that describes our series of points. If we assign a threshold of some large number, let's say 12, in this case we don't have sufficient intersections in our bin to say that the line belonging to this bin describes our data, and is therefore rejected. In the case of our gradient image, we'll have a threshold of 100, which I found to be an optimal value, such that the minimum number of intersections in Hough space for a bin needs to be 100 for it to be accepted as a relevant line in describing our data. The 5th argument is just a placeholder array, which we need to pass in, so just declare an empty array. Not much to it. The 6th argument is the length of a line in pixels that we will accept into the output, which we'll declare as a keyword argument. Min line length is equal to 40. So basically any detected lines traced by less than 40 pixels are rejected. And lastly, there is the max line gap keyword argument, which we're going to set equal to 5. This should be capitalized. This indicates the maximum distance in pixels between segmented lines, which we will allow to be connected into a single line instead of them being broken up. That's all, guys. We just set up an algorithm that can detect lines in our cropped gradient image. Now comes the fun part, which is to actually display these lines into our real image. What we'll do is we'll define a function, def display lines, which takes in an image onto which we'll display the lines as well as the lines themselves. And before giving this any logic, we're going to go right back here and set line image equal to the return value of our function, which we're going to specify momentarily, but we'll just set it equal to the return value for now. Display lines, pass in our lane image, as well as the detected lines. And back to our function, similar to what we have in region of interest, we'll declare an array of zeros, line image is equal to np.zeroslike, with the same shape as the lane image's corresponding array. So it will have the same dimensions as our image, although its pixels will be completely black, as all of them will have 0 intensity. And now all of the lines that we detected in our gradient image, will display them onto this black image. This is a 3-dimensional array. To check if it even detected any lines, we have to check if the array is not empty. That is, if lines is not none. If it's not empty, we'll loop through it for line in lines. If you print each line that we iterate through, print line. Back to our terminal, run Python, lanes.py. If you print each line, notice each line is a 2-dimensional array with 1 row and 4 columns. What we're going to do is reshape every line into a 1-dimensional array, such that line is going to equal line.reshape, and we're going to reshape it into a 1-dimensional array with 4 elements. And you know what? Instead of setting line is equal to line.reshape4, we can simply unpack the array elements into 4 different variables: x1, y1, x2, y2. And now what we'll do is take each line that we're iterating through and draw it onto our blank image. Thanks to OpenCV, we can write cv2.line. This function draws a line segment connecting 2 points. We'll draw our lines on the line image, the black image we just created. The second and third arguments specify in which coordinates of the image space that we want to draw the lines. So the second argument will be the first point of the line segment, which is simply x1, y1. And the third argument is the second point of the line segment, x2, y2. All right, so we've specified the coordinates in which we want our lines to be drawn with respect to the image space. The next argument is what color we want the lines to be. So we'll specify a BGR color of 255, 0, and 0. This should result in a blue color since the red and green channels will have 0 intensity. And finally, the line thickness, which is going to have a value of 10. Obviously, the higher the value, the thicker the lines, and that is all. All of the lines we detected in the gradient image, in our cropped image, we just drew them onto a black image, which has the same dimensions as our road image. Now let's just go ahead and return the line image. Return line image. And over here, we're going to show the line image instead of cropped image. And back to our terminal, we'll rerun our code, python lanes.py. And as expected, it shows the lines that we detected using Hough Transform, and it displayed them on a black image. The final step is to blend this image to our original color image. That way, the lines show up on the lanes instead of some black screen. So what we'll do is we'll go back to our code and we'll set combo image. I'm sure I could have come up with a better name than that, but combo image is equal to cv2.addWeighted. And so what we're going to do with addWeighted is take the sum of our color image with our line image, which should now make sense to you as to why the background of line image is completely black, since that would signify pixel intensities of 0, and by adding 0 with whatever pixel intensities are inside of this image, inside of lane image, the pixel intensities for that image would just stay the same, it wouldn't change, because 0 plus anything doesn't really make a difference. It's only when we blend the pixel intensities of our lines to the original, that we'll see a difference since they actually have a non-zero pixel intensity value. Anyway, first argument is going to be the lane image. And we're taking the weighted sum between the arrays of these two images. We'll give our lane image a weight of 0.8. Basically, that's going to multiply all elements in this array by 0.8, decreasing their pixel intensities, which makes it a bit darker. It will be more apparent why we're doing this momentarily. The third argument is the second input array of the same size, and we know it's the same size because we gave it the same shape as our lane image array, but it's all zeros instead. But anyway, let's put our line image array, and we'll give that a weight of 1. Multiplying all elements in this array by 1. And now when we add these two arrays up, this one will have 20% more weight, which means that the lines will be more clearly defined when we blend the two images. This image is going to be a bit darker, thereby better defining the lines that we're blending it into. Finally, there's the gamma argument, where we can choose some value that will add to our sum. We'll just put a scalar value of 1. It won't really make a substantial difference. And that is all. We detected lines in the gradients, placed these lines on a black image, and then we blended that image with our original color image. So if we replace this with combo image, run the code, python lanes.py, indeed blended both of our images such that the lines are displayed right on top of our lanes. That is all for identifying lane lines. You learned how to identify lines inside of a gradient image with the Hough Transform technique, and then we took these lines, placed them on a random black image which has the exact same dimensions as our original road image. Thereby, by blending the two, we were able to ultimately place our detected lines back onto our original image. In the next video, we'll further optimize how these lines are displayed. In the last lesson, we detected lines from a series of points in the gradient image using the Hough Transform detection algorithm. We then took these lines and placed them on a blank image, which we then merged with our color image, ultimately displaying the lines onto our lanes. What we'll do now is further optimize how these lines are displayed. It's important to first recognize that the lines currently displayed correspond to bins which exceeded the voting threshold. They were voted as the lines which best described our data. What we'll do now is, instead of having multiple lines, we can average out their slope and y-intercept into a single line that traces out both of our lanes. Before getting into it, it seems that there is some inconsistency in the code. This should be image, so as to properly reference the argument, not lane image. And the same thing here. Make sure to reference the argument image, not the global variable canny. It shouldn't have made a difference since they both correspond to the same value. The same case for this one, but it's always good to be consistent so as to avoid bugs. Also, not a good habit to reuse variable names, so we'll rename this to canny image and change it over here accordingly. All right, we'll start this lesson off by going over here and setting averaged lines is equal to the return value of some function that we'll declare later on, average slope intercept, that will be our function name, and we'll pass into it our colored lane image as well as the lines that we detected. And now we'll simply define the function right on top, def average slope intercept with argument image and lines. And what we'll do first is we'll declare two empty lists. Left fit is equal to an empty list. Right fit is also equal to an empty list. Left fit will contain the coordinates of the averaged lines on the left, and intuitively, right fit will contain the coordinates of the line which will display on the right. What we can do now is loop through every line as we did previously, for line in lines, and reshape each line into a one-dimensional array with 4 elements, line.reshape 4, and now we'll unpack the elements of the array into 4 variables, where x1, y1, x2, y2 will equal the 4 values in the array respectively. Nothing new so far. These are the points of a line. When you're given the points of a line, it's very easy to compute the slope by calculating the change in y over the change in x, subbing that into our equation to then determine the y-intercept. Well, to determine these parameters in code, what we can do is set parameters is equal to numpy.polyfit. What polyfit will do for us is it will fit a first-degree polynomial, which would simply be a linear function of y is equal to mx plus b. It's going to fit this polynomial to our x and y points and return a vector of coefficients which describe the slope and y-intercept. The first argument is where you will place the x coordinates of your 2 points, x1, x2. The second argument is where you will place the y coordinates of your 2 points, y1 and y2. And we'll fit a polynomial of degree 1 to our x and y points. That way we get the parameters of a linear function. If you go ahead and print parameters into our terminal, pythonlanes.py, for each line that we iterate through, it prints the slope and the y-intercept. The slope is the first element in the array. The y-intercept is the second element. So what we can do is set slope is equal to parameters at index 0, and we'll set intercept is equal to parameters at index 1. And now for each line that we iterate through, we need to check if the slope of that line, does it correspond to a line on the left side or a line on the right side. To determine this, it's important to note that our lines, depending on which side they're at, are all roughly more or less going in the same direction. All the lines here are slanted a bit to the left, and all the lines here are slanted a bit to the right. Here's our image displayed with X and Y axes. Notice that in the image, the Y axis goes downwards along the rows. And if you remember from basic high school math, a line has a positive slope when Y always increases as X increases. So these lines would have a positive slope as their change in Y over the change in X would result in a positive value. Although for these lines, since as X increases, Y decreases, their slope value would therefore be negative since their change in Y over the change in X would result in a negative value. Final conclusion being, lines on the left will have a negative slope, lines on the right will have a positive slope. So what we can do is, back to our code, we can write if slope is smaller than 0, if the line we're iterating through has a negative slope value, we'll append it into the left list, leftFit.append, and we'll append each slope and y-intercept as a tuple. Slope, intercept. Otherwise, else, we'll append it into the right list. rightFit.append, slope, and the y-intercept. If we print the results outside of the for loop, print left fit, print right fit, back to our terminal, python lanes.py. Now we have a list that contains all of the slopes and y-intercepts of the lines on the left side, and another list that contains all the slopes and y-intercepts of the lines on the right side. What we want to do now is average out all of these values into a single slope and y-intercept. Back to our code, we'll do that for both sides, but we'll start with the left side. We'll set left fit average is equal to numpy.average, and we're going to average out all the values of our left fit, and it's really important that you specify an axis is equal to 0. Imagine this was an array of multiple rows and 2 columns. What we want to do is operate vertically along the rows to get the average slope and the average y-intercept, respectively. Do the same thing on the right side. Right fit average is equal to numpy.average. We'll do that for right fit with an axis is equal to 0. All right, we'll go ahead and print left fit average, print right fit average, and we'll go ahead and just label them for clarity, left and right. Back to our terminal. We get back to arrays. This array represents the average slope and y-intercept of a single line through the left side, and this array, the average slope and y-intercept of a single line through the right side. We're not out of the woods yet. We have the slopes and y-intercepts of the lines that we'll eventually draw, but we can't actually draw them unless we also specify their coordinates to actually specify where we want our lines to be placed. The x1, y1, x2, y2 for each line. So what we'll do is we'll define a function, def make coordinates, with argument image and line parameters with some return value. This return value is going to denote x and y coordinates of the line. So back here, we'll set left line equal to the return value of make coordinates. We'll pass in the respective arguments, the image, as well as the slope and y-intercept of our left line, left fit average. Same thing for the right line is equal to make coordinates, image, right fit average. Back to our function, we're going to unpack this list of 2 elements, whichever one that's being passed in, the slope and intercept into 2 variables. Slope intercept is equal to line parameters. We'll start with y1, the initial vertical position of our lines. This one is pretty obvious since we want our lines to start at the bottom of the image. Before we do this, if you go ahead and print the shape of the image, print image.shape into your terminal. We'll rerun this code. It prints twice since clearly we're calling the function twice, but regardless, recall that the shape corresponds to your array's dimensions. In this case, this represents the image's height, width, and number of channels. We're only interested in the height, which also corresponds to the bottom coordinate of our image, as demonstrated by matplotlib. A little counterintuitive that the highest value is on the bottom of the y-axis, but another way to interpret this is to have the y-axis going vertically downwards from 0 to 700, which makes sense since images are simply arrays of pixels and array indices are read from the top down. We'll set y1 is equal to image.shape at index 0, since that represented the height. And now y2 is going to equal y1 times 3/5. We'll make this into an integer type. And so essentially this will be 704 times 3/5, which is going to evaluate to 422, which means that both of our lines will start from the bottom at 704 and goes 3/5 of the way upwards up until the coordinate 420. All right, now x1 can simply be determined algebraically. We know that y is equal to mx plus b, so x is equal to y minus b divided by m if you rearrange the variables. So we can simply set x1 is equal to y1 minus the intercept divided by the slope. We'll make this into an integer as well. And the same thing for x2, except that we have to replace this with x2 and y2. Now that we have all of our coordinates, we'll return them as a numpy array, numpy.array, x1, y1, x2, y2. So both of our lines are going to have the same vertical coordinates. They're both going to start at the very bottom. But they're going to start at the bottom and go upwards 3/5 of the way up until the coordinate 424. But their horizontal coordinates are obviously dependent on their slope and y-intercept, which we calculated right here. We finally have our lines. We can return them as an array. Return numpy.array left line and right line. And now comes the fun part, which is instead of our line image being populated by the Hough detected lines, we're going to pass in the averaged lines. If we show the line image instead, run the code, this looks a lot smoother. Instead of many lines, they were all averaged out into a single line on each side. Back to our code. Obviously, we're still blending the line image with the color image. So let's show that instead. Combo image. Back to our terminal. We'll rerun this. And it displays our two lines. On our two lanes, we took the average of our lines and displayed one line on each side instead. This looks a lot smoother than earlier. One more thing before we end this lesson is that previously we were passing in a three-dimensional array, the Hough lines, into our display lines function. But now we're passing in the average lines that we created, and we know that when we iterate through over this lines array, each line is already a one-dimensional array, so there's no need to reshape it into one. It already is one-dimensional, so feel free to remove the reshape for. It's just extra code. Doesn't really make a difference whether you have it or not. And better yet, we can simply unpack each line into 4 variables over here and delete that. And that is all. Let's rerun it to make sure we didn't make any mistakes. And everything still works out accordingly. In the next lesson, we'll use the code that we currently have and take it up a notch by identifying lane lines in a video. Welcome to your last lesson of this section. In the last lesson, we finally finished our line detection algorithm and identified lane lines in our image. What we'll do now is use that same algorithm to identify lines in a video. This is the video, and we'll use the algorithm we currently have to detect lane lines in every single frame. This video you can access from the following GitHub link, and now this GitHub link you'll find in the description below, labeled as video link, or you can feel free to just type out the link, it's up to you. Now anyway, once you're on this page, click on test2.mp4 and download it. Alright, and upon downloading it, make sure it says test2.mp4 so as to stay consistent with the videos. And once you download it, wherever you have it downloaded, drag it into your project, Finding Lanes. If you are using the Atom text editor, don't try and open the video with Atom, otherwise it will freeze. Alternatively, we could have placed this video in desktop or some other directory and just referenced its path, but we'll go with this for now just to keep things quick. Regardless, to capture this video in our workspace, we need to create a video capture object by setting a variable name. Cap is equal to cv2.video capture, and we'll capture the video test2.mp4. And while cap.is opened, this returns true if video capturing has been initialized. We'll enter into a loop where we will first use the read function, cap.read, to decode every video frame, and what this returns is two values which we can unpack. The first value is just a boolean that we're not currently interested in, so leave that as blank. The second value is the image, the frame that's currently being projected in our video. And it's the current frame of our video where we'll be detecting lines. So what we'll do is actually copy and paste the code, the algorithm we already have for detecting lines. We're not going to do it all over again. And wherever it says lane image, we're going to replace that with the current video frame. Over here, here, and here as well. Make sure to get all of them, otherwise your code will not make any sense. Pretty easy. All we did was apply the algorithm we already implemented, but instead of a static image, we're doing it on a video, since we're not working with images anymore. You can go ahead and comment out this code or delete it, it's up to you. I myself will comment it out. And now with imshow, we're still showing the current image that's being processed. As for wait key, if we leave this at wait key 0, you're going to be waiting infinitely between each frame of the video, so your video would just freeze up. Instead, we want to wait 1 millisecond in between frames to then display the next one. Now, before we add any logic to break out of this loop, let's just run the code by going to our terminal and running python-lanes.py. And alright, it identifies the lines in every single frame of our video. That's pretty cool. And this is nothing new. It follows the exact same process as how we detected lines in the image. We're still applying the Canny algorithm to get the gradient, detecting lines with Hough Transform, and then averaging them out. Except now it's being done in every single frame of the video, repeatedly inside of a while loop. That is all for this section. Now just to finish this lesson off, if I rerun the code and try to close the video, it doesn't work. We need a way to actually break out of this for loop and not just wait until the video is complete for it to dismiss. So we'll go back here. Upon pressing a keyboard key, we want the video to close. So we'll put this inside of an if statement such that we're still invoking the wait key function. We mentioned that it waits 1 millisecond in between frames, but what it also does is it returns a 32-bit integer value, which we can compare to the numeric encoding of the keyboard character that we're going to press. The numeric encoding we can obtain from the built-in function ord, and the keyboard character that we're going to press will be Q, and we'll just set a comparison operation between the two. Ultimately, when we press the keyboard button Q, the comparison of these numbers will evaluate to true, and once they are equal, we'll break out of the loop. And once we break out of the loop, we'll close the video file by calling cap.release, and we'll also call cv2.destroy all windows to destroy the window that we're currently on, to close it. Rerun the code, python-lanes.py, press Q, and everything works fine. If the keyboard action did not work out for you, a common trick is to apply a bitwise AND operation with the hexadecimal constant 0xff. Just know that this operation, it masks the integer value we got from wait key to 8 bits, which ultimately just ensures cross-platform safety when making our comparison. It's still the same concept as earlier, since when we press Q, this comparison still evaluates to true, breaking us out of the loop. Rerunning the code, everything should still work as expected. That is all for this section. We used Canny to convert our color image into a gradient image, and from the gradient image we detected the most relevant lines, averaged out the lines, and then displayed them on the image that's currently being processed. In the near future we'll be using a more advanced technique to detect lanes, but for now this is pretty awesome. Great job on making it this far. And that is all. To access the complete self-driving car course, where you'll learn to build a fully functional self-driving car with deep learning alongside computer vision techniques, it's accessible within the link in the description below. I'll see you in there.